Thank you, Luis, for the kind introduction, and thanks the organization for the opportunity to be here. Yes, I'm going to tell you about reinforcement learning, which is like a hot topic in research these days. And the way I will structure this talk is the following. I will split it in I will spend a few minutes to give you a refresher of the basic concepts of reinforcement learning so that everyone is in the same page. I will then list the challenges that we face on trying to apply reinforcement learning in real-world problems. And then I will conclude giving you some pointers to promising research directions that are now very active to overcome these challenges. So reinforcement learning is really a framework in which you are trying to dealing with the following problem. You have an agent that is interacting with an environment, and at each time step, the agent sees some observations, and it has now the opportunity to take some action. When it takes this action, the environment will be modified, maybe as a consequence of your action, or maybe just because there are other things going on. And so you will get new observations. In addition to that, you will also get a reward. So a reward is just a scalar value, could be a negative, 0, or positive value. And in fact, the goal of your agent is to learn to behave. So to find a good policy of behavior, this is just a function that decides for the current state or observation which action it should take, with the goal of maximizing a return. And the return is just the sum into the future of the rewards you get. Typically, there's also a discount factor to give more importance to immediate rewards than things into the future. But really what you want is to maximize this long-term return, like this. You are not really just trying to maximize for immediate rewards or short-sighted strategy. Really, you want to have a long-term return. The way I like to contrast this with supervised learning, which is probably the field of machine learning most of you are more familiar with, is the following. So imagine you have a navigation task. So for example, there is an agent that needs to reach some goal. In here could be this green circle. The way you would solve this with supervised learning would be the following. You would need data annotated by someone that already knows what is the solution for this problem. And it would be things like, okay, if you are here, go forward, then turn left, go forward, jump, whatever, and okay, now you got to the destination. So this is like really specific supervision on how you should do. And it's great for problems in which you know the solution already, and humans can provide it, and now your system just needs to replicate this, right? In the reinforcement learning setup, the signal you get to learn is different. It's a bit, in some sense, weaker. So what would happen is that the agent would have to start doing some trial and error. He would have to start moving around. And the feedback you would give is something like more, okay, you are not going in the right direction. It's getting cold. You try something else. Oh, you're getting hot, getting cold, getting cold. And so by trying things out and getting this feedback, you could still reach the goal. Obviously, there's different levels of detail in this reward you get. It could be very sparse, so you basically see zeros everywhere until you reach the goal, but this task will be much harder to solve. Or you could get this much more richer of like how far you are from the goal. So that's a contrast, to reinforce, supervised learning. Because you have to do some trial and error, RL has a very specific problem to deal with, which is this trade-off between exploration and exploitation. So if you decide to try something new that you never tried before, you are exploring. It's possible that by doing this, you get higher rewards that you haven't achieved in the past. However, you are incurring the risk of getting less rewards or even doing something unsafe. On the other hand, you can decide to exploit, which is taking the action that you already tried in the past and work relatively well. However, the risk is that if you always do exploitation moves, you might be missing something better, right? Maybe if you tried something different, it would work, you would find even a better solution. So now you have the big picture. So the promise of reinforcement learning is really the following. You just need to specify what you care about. And this is done by you defining the problem setup and the rewards. And now you let the system learn and improve by itself, and improve to levels that could be superhuman. Even the best humans could not do as well. And this is exactly what has been happening in the last, let's say, 5 years in the games domains and simulations. So in particular, DeepMind, where I used to work before, and OpenAI have become very famous for applying deep reinforcement learning. So it's reinforcement learning with function approximations like deep neural networks to solve very challenging games. The first impressive result was in this Atari console of games, in which you have like 50 different games that are available, and a single neural network architecture with the same hyperparameters, the same algorithm, learned to play all of them, and most of them to a level beyond human level performance. You also saw the impressive results with AlphaGo, playing the game of Go. And more recently, impressive results in Starcraft and games like DOTA 2. Well, having said that, what we really, really want is to have the same level of success in real-world problems, right? There's a lot of things we would like to be doing better, like in robotics, in recommender systems, and so on, that you would like to benefit from the same techniques. And here, the fact is that we only had some partial successes so far. So my colleagues at DeepMind, for example, we collaborated with teams at Google, for example, for controlling the cooling of data centers. And we could show that by using some concepts from reinforcement learning, you could have a control policy that would use less energy to achieve the same goals. The same thing about recommender systems. However, I must tell you that these are not yet the same algorithms that you are able to use in games. And that's what I want to explain today. So there are a few challenges. I will briefly start by naming some organizational problems and engineering, and then focus mostly on the research problems. In terms of organization people factors, I would just highlight these. There's still a bit of unawareness of the RL potential, right? Very few people know that RL can bring you even to superhuman level performance. There's definitely shortage of RL experts, and maybe they will concentrate in the big companies. But there's also a bit of risk aversion to experimentation, right? If you need to have a system that does a little bit of exploration, a little bit of trial and error interacting with your users, there's still a little bit of concern of doing that. In terms of engineering, because it's not yet very mature in the industry, there's no really standards for, let's say, data logging. There's no very well established libraries of frameworks. And again, if you have let's say an online service, typically they don't still support this kind of exploration that you do at serving time. One engineering challenge is that you might think it's hard is actually not a problem. So scalability has proven to be something relatively easy to do with the reinforcement learning because it's highly parallelizable. So instead of having one agent interacting and learning from the environment, you can first decouple things into actors that interact with the environment to collect data, and then learners, which they share some parameter server, representing a neural network, and they can process the data for learning. And then you can make how many replicas of this you want. So you can have hundreds of actors, hundreds of learners. So these days, people are able to learn at incredible speeds with reinforcement learning. So this is actually not a problem, unexpectedly. However, there's a series of research problems that are still open, and a lot of my colleagues that do research at Google and DeepMind, they focus on this. One of them is sample efficiency. So if you see this plot during training of a state-of-the-art or a few state-of-the-art algorithms in deep reinforcement learning, you see in the x-axis is the number of millions of frames. And for the algorithm to reach the maximum performance, it had to go over 200 million frames. You can imagine that if you would need to learn in a real system, for example, controlling a real robot, 200 million steps could represent weeks of data. And in that time, I mean, you cannot just wait for the robot to be there and it will break and so on, right? So we need algorithms that are much more sample efficient. This is really an important thing that needs to come. Another one that is extremely important is safe exploration. So I mentioned in the beginning that RL has to deal with this exploration problem, trying things out. And one of the basic exploration strategies that are used in the literature is called this epsilon greedy. So this just means that most of the time you take the action that you believe that will lead to the most reward. So you are being greedy. But for a small percentage of the time, you will take a random action. This will allow you to explore a bit. However, you can do this in games, right? Because the worst that can happen is that, okay, game over, you start again. And it's a simulated environment, nothing happened of consequence. But if you are dealing with real systems that could be robots or self-driving cars or things like that, even recommender systems in which you are recommending things to your users, you don't want the experience to degrade for your users, right? Like you don't want to start showing recommendations that are really relevant. And on top, and if it's like really a physical system, you don't want to have to break things, right? Or cause physical harm to people. So this is a very important open problem in research, is like, how can you still try things out, but in a safe manner? Because of these two initial constraints I told you about, that it's not that easy to learn directly on the real systems, one typical thing that applied teams ask is like, well, if you want to do RL, why don't you use the logs that I have from the past log data and start learning from there? Well, you can do that, but again, it becomes a challenging research problem, right? Because in typical RL, you have this freedom of learning online. You are learning about the data you get. It's, let's say, you are evaluating the policy that is used to collect the data. You get this fast feedback loop. You can explore the state space and so on. If, however, you are restricted to learn from logs, you have to learn offline. It's sometimes you need to learn from data that was collected from a different behavior policy than the one you want to implement. And then it makes it much harder to estimate the quality of your new policy because you don't have real data from it. And in addition, you cannot explore because the data is already pre-collected. You cannot try new things. So this is actually an area in which I did some recent research because it's a very common request from applied teams. Another difficulty is the dimensionality or the size of your action space. So I said before that your agent can decide which action to take. So in some environments like that one I told you in the beginning, the Atari, you can control a joystick and press some buttons to play the game. There are only 18 possible actions you can take. In Go, it's a board game, you have 361 places where you can put your stone. These are relatively small action spaces, but if you have a recommender system, for example, if you are YouTube and you want to recommend the next video to watch, you're going to have hundreds of millions of possible actions you need to take, right? You can take. So this brings the learning process to a completely different regime, right? So again, this is an active area of research, how to do RL with these very large action spaces. And likewise, if you are dealing, let's say, with robotics, the action space is actually continuous, right? It's no longer a discrete set of options you can take. It's like the angles of the joints that you will apply to the robot. So it's again requires a different kinds of algorithms. There's also the problem of partial observability. So in reinforcement learning, you often assume that your policy just needs to look to the current observations or to have an idea of what is the state of the system. So that you can, this is called the Markovian assumption. So everything that happens into the future just depends on the present. However, if you are dealing with partial observability, so you only are able to see what is ahead of you, you don't see what is behind, there's things like that, there's this additional complexity of your system need to create a representation that also memorizes something from the past so that now, indeed, you respect this Markovian assumption, like the future only depends on this representation you have. And Another important aspect for RL in the real world is robustness. So very often you train your system in an environment, but when you deploy it, it will have small perturbations. So imagine it's a robot. There will be small defects, like the friction in some joints will change, some engine will get damaged. I don't know, temperature is different from what you expect. So if you trained a policy in certain conditions and it will be exposed to different ones, you don't have by default a guarantee that this will work out smoothly, right? So interesting research now is how can you train reinforcement learning agents that are exposed to a variety of conditions, and the policies they learn are robust to these perturbations, so they will do well in any of those, rather than being specific to a very specific to a set of conditions. We saw also in the previous talks that often people also care about explainability of your model and also uncertainty estimation. So these are actually not specific to reinforcement learning. They apply to any machine learning application, but I thought I would mention here because it's also a common request. If you go to, like my previous team did, if you go to start operating the cooling of a data center and they have experts doing this, they will feel much more comfortable if your system is able to explain to them why it's now suggesting to take these actions rather than the ones we are used to. And it's very important if you have some idea of the uncertainty, right? If you can say, well, I'm suggesting this, but I'm not really sure it makes sense, or yeah, I know this will work, right? So these are very generic problems for applied ML. So now I just want to conclude with pointing you to 3 promising research directions that will solve at least some of these problems. One of them is actually bringing ideas from supervised learning. So it's learning from expert demonstrations. So if you happen to have a domain in which you already have experts that operate the system, you can collect this temporal sequence of actions they did, and you first do supervised learning on those. And then you can go beyond their performance by starting doing reinforcement learning from there. But at least you don't start from scratch. So the research that has been happening has had some success with this, but it's still tricky because neural networks often quickly forget what they learned in the past. So sometimes there is a bit of a dip when you transition from the pre-trained model with the human data to doing RL. So there's still some work to be done there. Another approach in which particularly OpenAI has been very strong is actually bridging the gap between reality and simulation by actually doing very good simulators. So they have these results recently in this robotic hand that controls this Rubik cube. And the control algorithm for this task, which is quite hard in terms of dexterity of like the robot, was trained purely on simulation. So they have a very accurate simulator of this hand. And to make sure that when they run the policy in the real world, this still works, what they do is that they inject a lot of randomization during training. So they change the colors of the hand and the background, the lightning. They change maybe a little bit how long are the joints, what are the frictions, and so on. That, again, when you train on these simulated environments with this kind of ball of perturbations, you have the hope that this will somehow include the typical perturbations you will see in reality. And they have had quite a lot of success with this. But there are other approaches like pre-training in simulation and then doing a bit of training in the real world in which you need fewer iterations. That also works. And my favorite one, which is like, I think, the holy grail of reinforcement learning, is model-based RL. Is the field of reinforcement learning in which, rather than trying immediately to learn a control policy, you first try to learn the physics of the world, how things work, how things change as an effect of your actions. If you have an idea of this, then you can do most of your learning basically in your head, right? You can plan just using the model you have of the world without having necessarily to interact with it, or not as much. So this improves a lot in sample efficiency. It will help with the safe exploration, because if you can plan what happens by applying those set of actions, you can notice, oh, this will be dangerous, so I'll not try it. it will be much easier to do multitask. So if now you change, oh, now the task is different, do this, you already know the model of the world, you can learn much faster. So keep an eye on this. And I really just want to conclude with a summary of what we saw today. So reinforcement learning really holds the promise of going beyond human level performance, which in some fields is going to be super useful. So far, the successes have been restricted mostly to games, but there are a lot of promising research directions that will bring us closer to real-world applications. So I believe it's coming. Thank you so much.